Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to find the empirical formula of a substance. So let's get into this. So the first thing we need to do is determine or define what we mean by empirical formula and compare that to what we mean by a molecular formula. So an empirical formula is the simplest, most reduced version of a formula. So it's the formula that has the smallest whole number ratios possible for that particular formula. And this is and then the molecular formula is the actual formula of the substance. So if you were to analyze that actual substance, you would find that the molecular formula would be such and such. So this version is the actual version, the actual number of elements that are in that compound, and this may or may not be the simplest, most reduced form. This is going to depend on the specific formula. So the best way to kind of clarify this is to go over an example. And here I have the example benzene. This is the actual molecule of benzene, or an actual picture or drawing of the molecule of benzene. This is what it looks like. And so you'll notice that in the molecule itself, it has 6 carbons and it has 6 hydrogens. So that's what's really in the molecule itself. And so the molecular formula would reflect that. So here, the molecular formula has C6H6. So that is what is actually in the formula itself, the actual substance. So that's the molecular formula. Now, the empirical formula is the reduced version of that. If you were to reduce everything or simplify that version to simple whole number ratios, to smallest whole number ratios, excuse me, then what you would see here is that the ratio of carbon to hydrogen is 6 to 6. And if we reduce that, that would be 1 to 1. So we go to 1 to 1 here. We don't write the ones in our formulas, but they're there, right? So I have 1 carbon, 1 hydrogen. So this would be the empirical formula for benzene. It's the reduced form of this. So this is the molecular formula, which shows you exactly how many of each kind of atom that exists in the molecule itself in reality. And this is just the simplified version of it, which we call the empirical formula. Well, what about other examples? What about ions versus other covalent compounds? So I'll go over that in just a second. Okay, so what about ionic formulas versus covalent formulas? So the thing about ionic formulas and ionic compounds is that they are always written in the empirical form. So you always get empirical formulas from your ionic formulas. There is no reducing because they are already completely reduced, and that's just the way you write ionic formulas. And the reason for this is because we don't really have molecules for ionic substances. We always have what are called formula units, and that is because, as you know, salts are made up of crystals. Those are ionic substances. Substances are crystals, and so the crystals are made up of hundreds and thousands of different ions that have a repeating pattern. And so there's no distinct molecule that you can point to, since it's a three-dimensional crystal structure of alternating positive and negative charges. So since we can't really choose or pick out what the actual molecule is, we don't use the word molecule, we just say a formula unit. And basically, that formula unit ends up being the ratio of the positive ion to the negative ion. So remember, for your ionic substances, you have to write the formula as a balance of charge. So, for example, we have sodium here. Sodium has a +1 charge, and the chloride ion has a -1 charge. And so you only need one of each to balance the charge, and so the ratio is 1 to 1. Here, magnesium has a +2 charge, And so you need two chloride ions to balance the charge. And so it's just 1 to 2, and that's the way we write it. Now, that means if you have two magnesium ions, then you need four chloride ions to balance the charge. So it would be Mg2Cl4. But we don't write it like that. We just write it as the simplest whole number ratio. So that's why ionic formulas are always empirical. But for covalent formulas, you have molecules that actually have a real certain number of atoms in the molecule. And so sometimes they're going to be empirical and sometimes they're not. So the actual formula, so here are three examples. So the molecular formula for water is H2O. Water actually has two hydrogens bonded to one oxygen. So, and you'll notice that it's already in the simplest whole number ratio. You can't reduce 2 to 1 any more than it already is. So it's already in the simplest whole number ratio. So the empirical formula will be the same. Here we have the molecule of glucose. And so this is sugar. And so that has the formula of C6H12O6. And so you can, in fact, reduce this. So sugar or glucose already actually has 6 carbons, 12 hydrogens, and 6 oxygens in it. So this is the molecular formula. But we can write this as the empirical formula of CH2O. So you can reduce the 6 to a smaller whole number ratio, 1 to 1. Now, the important thing or an interesting thing to point out is sugar, this simple sugar, we call them carbohydrates. Why do we call them carbohydrates? Well, you can see in the empirical formula in here that we have carbon, carbo, and we have H2O, water, which is hydrate, right? So carbohydrate, like when we say, okay, I need water, so I need to be hydrated, right? So the hydrate part of the word refers to the H2O in the empirical formula, and the carbo refers to carbon. So carbohydrates. Okay. And here we have a complex sugar. This is like something like sucrose. And so here we have 12, 22, 11. And so because of the 11, we can't reduce this anymore. So that's the empirical formula as well. Okay, so now that we have under our belt this distinction between molecular formulas and empirical formulas, let's go over how to find the empirical formula of a substance when you're given the percent composition of that substance. So give me 1 second and we'll get into that. Okay, so when it comes to determining the empirical formula, there's a couple of ways to go about this. One of the most common ways is you're given the percent composition of a particular substance. So they'll say, okay, you have this substance, for example, let's say aspirin, and they say, oh, it's got 22.5% carbon, and it's got 32.69% oxygen, and it's got 5.62% nitrogen and all the rest of it, right? So they break it down and they say this substance has these percentages of these elements. And they want you to find the empirical formula. So the steps you want to go through are pretty simple. So I'm going to lay them out here and then I'm going to go over some examples. So the first step is always when you're given, in the case that you're given a percent composition, since percent means per 100, right? Then what you can do is you can assume that you have 100 grams of the substance. You can assume any amount you want, right? It's just easier to use 100 grams because the percent of 100 out of 100 grams is just the percent that you were given. So you're just going to change your percentages into grams. So for example, if I'm told that I'm given 30%, I'm given that 30% of my substance is carbon, then I assume, oh, if I have 100 grams of this substance, that means 30 grams of it is going to be carbon, right? So you're just going to assume you have 100 grams and then just change the percentages to just grams. That's the first step. Second step, you're then, now that you have grams, right, you can use the molar masses to convert to moles. Well, why do I want to convert to moles? Well, remember that the formula that you have of a substance, the subscripts are molar ratios, not gram ratios, right? So if you're going to find the empirical formula or any formula for a substance, you need a mole ratio so that you can compare the moles of the different elements and try to get a ratio from that. So you need moles. So the second step is to convert your grams that you have to moles. And you're going to use the molar masses of the elements to do that. So if I have 30 grams of carbon, I'm going to use the molar mass of carbon to convert the grams to moles. So I want to get moles for each of my elements, so that way I can use the moles as subscripts. Remember, the subscripts in your formula are mole ratios. So in water, for example, we said water was H2O. That means that in water, for every 2 moles of H, hydrogen, you have 1 mole of oxygen. So they're mole ratios. So you need moles. So step 2, convert your molar masses, convert your grams to moles using the molar masses. And then once you've got the moles, you're going to write what is called a pseudo-formula using those moles. Now, the moles that you're going to end up with are not going to be whole numbers. They're going to be like fractionals, like 0.2356 moles, right? It's going to be a weird number. But you're going to write them as subscripts anyway, because you're going to end up with subscripts in your formula as moles, right? So the moles are going to end up as subscripts either way. So I like to just write the formula with the moles I have right now. So I'm going to write the pseudo formula using the moles as subscripts that I have. And then I'm going to work on getting simple whole numbers. And that's the next few steps. So step 4, once I have my pseudo formula, I'm going to find the smallest mole subscript, whatever subscript that is the smallest, and I'm going to divide the other subscripts, the other moles, by the smallest subscript. And so at that point, after I divide each one by the smallest, I'm going to check to see if I have a whole number. Well, why do I divide by the smallest? Well, the reason is because I'm trying to get a ratio, a whole number ratio between one of them and the others, right? And the best way to do that is just find the smallest and divide the others by it. And if they divide evenly, then you've got your whole numbers. So that gives me the steps 5A and 5B. So after you divide by the smallest one, if you have all whole numbers, you're done. So you should, all your subscripts should be whole numbers, and you're done. You've got your empirical formula. Now, that doesn't always happen. You might divide by the smallest number, and one of them will be a fraction, right? So instead of 2, you've got 2.5, or instead of 3, you might have 3.33, or something along those lines. If you've got a fraction, then the next thing you need to do is 5B. If you have a fraction, you're going to multiply by a factor to get rid of that fraction, and then you'll be done. You'll have your empirical formula. So for example, if one of my mole amounts ends up, after I divide the subscripts by the smallest subscript, and I end up with one of my mole amounts is, or one of my subscripts is 2.5, well, 0.5 is 1/2. Well, how do you get rid of 1/2? Well, you multiply by 2. But you're not going to multiply only that one by 2. You're going to multiply all of the subscripts by 2 to get rid of that particular fraction. And so then you'll have your all your subscripts in whole numbers. If one of your subscripts has a fraction of, say, let's say it was a 6.33, well, the 0.33 is 1/3, right? So then you're going to multiply everything by a 3. If you have a 0.75, right? That fraction you could divide by 4, right? Because that's 3/4 is 0.75, or 0.25 would also be 1/4. So you multiply by 4 to get rid of that fraction. And then you're done. You should, at that point, have your empirical formula. Okay, well, those are the steps. I hope I explained it clearly enough, but I always like to do examples to make it clearer. It always helps to do in examples. So now I'm going to do some examples to show you how it's done. Okay, so here's my first example. So here you have, you're given that adipic acid contains 49.3% carbon, 43.84% oxygen, and 6.85% hydrogen by mass. And they want you to give the empirical formula. So let's go through the steps. So they give me percentages. So the first step is to convert the percentages to grams, because I'm assuming 100 grams, right? So first step, I have for carbon, they're giving me 49.32%. Well, I'm just going to convert that or change that to 49.32 grams. So I have that many grams of carbon out of 100 grams of my adipic acid. And I do the same thing for the other two. So I have 43. So for oxygen, I have 43.84% oxygen. I'm just going to change that to grams. So that's going to be 43.84 grams of oxygen. And then in hydrogen, they're giving me 6.85%. And so out of 100 grams of my adipic acid, that's going to be 6.85 grams. So all I've done is just change the percent to a gram. Now that I have the grams of each one, now the second step is I want to convert these gram amounts to moles. I'm going to use the molar mass of each element. So I'm going to take the 49.32 grams of carbon divided by, I'm going to put that out 1. And then I'm going to use the molar mass as a conversion factor. So I have 12.011 grams of carbon per 1 mole of carbon. So grams of carbon cancel out. And then I got my moles. And the moles that I calculated is 4.107 moles of carbon. I do the same thing for oxygen. So I have 43.84 grams of oxygen over 1. The molar mass of oxygen is 16, so 16.00, or your periodic table might say 15.9994. It doesn't matter if you round that. So I'm going to just round. So 16.00 grams of oxygen per 1 mole of oxygen. So grams cancel out. And then I end up with a 6.78. So 6.78 moles of oxygen. And finally, I have my hydrogen. So I'm going to take my 6.85 grams of hydrogen, use the molar mass of hydrogen to convert. So that's going to be 1.008 grams of hydrogen per 1 mole. 1 mole of hydrogen on top. So grams cancels out. And I end up with 2.74. So 2.74 moles of hydrogen. So now I have my moles of hydrogen, my moles of oxygen and carbon. So now, because I want an empirical formula, I need a mole ratio. I need a formula that has subscripts as mole ratio. So I'm going to write the moles that I have here as a pseudo formula right away. these mole amounts are not pretty, they're not whole numbers, but I'm going to write them as subscripts anyway, and we can work to get them into whole numbers. So my pseudo formula is going to be C for carbon, so I'm going to write 4.107, and then I have oxygen, so O, and the subscript is going to be 6.78, and next would be hydrogen, which the subscript is going to be 2.74. So it's a pseudo formula because it's written like a formula, but you'll notice that my subscripts are not whole numbers. So now we need to work to get them into whole numbers. The next step you're going to do is you're going to take the smallest number and divide all of them by that number. So here, the smallest number is 2.74. So I'm going to divide all of these by 2.74. So I divide this by 2.74. And you'll notice here that I'm going to get a whole number 1. Well, the goal is to divide these and hopefully get a whole number as well. You don't always get a whole number, but sometimes you do, right? So let's see what happens. So maybe I might get whole numbers by dividing these by 2.74. So this will be 2.74. And so when I do the calculation, this is what I end up with. So these end up with, I'll get carbon. Carbon now is 1.50, and hydrogen, or let's do oxygen. Oxygen is now 2.47, and this is of course 1. So you'll notice that I have still fractions here, right? So I'm not done yet. So now I got to look at my fractions and see if I notice that there's a simple fraction here that I can multiply by a factor. And so you'll notice that this is 0.5, which is 1/2. So if I could multiply by 2, then I could get rid of that fraction and I'll get a whole number. Now this one is 2.47. But you'll notice the 47 here is pretty close to 0.5, right? So it's okay to round this. So if you get something that's like 0.47, 0.48, 0.49, something really close to 0.5, then round it to that nearest fraction. So for example, if you got like 0.32, well, 0.32 is really close to 0.33. 0.33 is 1/3, so you can multiply by 3, right? So don't be afraid to round if it's really close. Now, most of the time they'll be really close, but I would say if you got something like 2.45, that's pretty far, and so I would double check your calculations. I wouldn't round that to 2.5, right? But 2.47 is pretty close. That's close enough to round. So then, basically what I'm going to do is I'm going to, sorry about that, I'm going to multiply all of these by 2. And so this is going to be, if I round this to 2.5, right? So this is 2.50. Now I multiply everything by 2. 1.5 times 2 is 3, so that becomes C3. 2.5 times 2 becomes 5, so that's going to be O5. And then 2 times 1 is 2, so H2. And now I have my empirical formula. So this is the empirical formula for adipic acid. So that's my one example, and let's do another example. Okay, welcome back. So problem number 2. Now, here's the problem number 2. Adipic acid contains 49.32% carbon, 43.84% oxygen, and 6.85% hydrogen by mass. What is the molecular formula? by the way, the molecular mass of adipic acid is 146 grams per mole. Now you're probably wondering, Mr. Koval, this is pretty much the same problem. What's different? What's different here is they're not asking you for the empirical formula, but the molecular formula. However, in order to get the molecular formula, you have to find the empirical formula first. So you have to do those steps again, which we're not going to do. I'm not going to go over them, but there is the exact same steps. So you got to find the empirical formula first using the steps we just went over. And then you got to use that to find the molecular formula. And here's how. So assuming we went through all those steps, we arrive at our empirical formula. Now, what did we say before about the relationship between the molecular formula and the empirical formula? The relationship is that the empirical formula is a reduced version of the actual molecular formula. So they're going to differ by some sort of factor, right? A factor of 2 or a factor of 6. So for example, if you remember, benzene has a molecular formula C6H6. The empirical formula is CH. The difference here between these two is a factor of 6. I have to multiply this by 6 to get this. So the difference between the molecular and the empirical formula is going to differ by some factor, and you have to find that factor. Well, look here. So the mass here, the amount of mass here of carbon, and the mass amount here is carbon, is what? A factor of 6. And the same thing here. The mass of hydrogen here and the mass of hydrogen here differ by a factor of 6. So the whole molecule in the empirical formula, the mass of the empirical formula compared to the mass of the actual formula is going to be differ by a factor of 6. So if we know the masses of our empirical formula and we know the molar mass of the actual formula, we can find the factor that we need by dividing. And that's what we're given here. So we're given the molecular mass of the actual substance is 146 grams per mole. So this is the formula mass. This is the molecular mass of the actual formula. So all we need to do now is calculate the formula mass of our empirical formula. So let's do that. So we're going to compare this. So carbon. So for carbon, we have 3 carbons. So we're going to multiply that by 12.011. And what do we get for that? Or we're going to, well, let's add. So we're going to, and then we're going to, for hydrogen, we're going to multiply 5 times 1.008, and this is grams per mole. And then for oxygen, that's going to be 2 times 16.00 grams per mole. And so when we do this calculation, we just add it up and we get the total is going to be 73.08 grams per mole. So now we have the molar mass of our empirical formula. They gave us the molar mass of the actual substance. So this is the molar mass that we would calculate if we knew what the molecular formula is. But we don't know what the molecular formula is. That's what we're trying to find. But we know that the difference between the molecular formula and the empirical formula is a factor. So instead of using the formulas, we're just going to use the masses. So we're going to divide the larger mass, right? Because the larger mass is associated with the the molecular formula. So that's going to be 146 grams per mole. And we're going to divide that by our formula mass for the empirical formula we found. So we're going to divide that by 73.08 grams per mole. And what you notice is that this is approximately 2.